right. Howdy, everyone. So some things you're going to be seeing, which I am putting up. I'm putting up all of the stuff in Pearson for the rest of the semester. I have just done that for my 162, my 092 class. I need to do it for this class and my Phys 101. So you'll be seeing all the homework for the chapters that we're doing, plus the next two exams. And yes, there's two exams. There's going to be one on chapters 5 and 6, and we're finishing chapter 6 today. And then we're going to do chapter 7 and chapter 9. And so there'll be a short final exam that has the 7 and 9 material on it. There's also a... well, you'll see when we do chapter 9, linear regression is not easy to do by hand. Without like graph paper and loads of plotting points and specialized rulers, but it's immensely easy to do in Excel or sheets. And so I have a small Excel demonstration that works through that I will be posting. I think I will email out the PDF of that to everyone, and I will also try to put it on Blackboard. I do not like Blackboard. We know this, we see this. I tend to use Blackboard as a messaging system coming across. So you'll see two more exams, but everything will be up on Pearson. I almost have all the homework in right now, and I just need to switch it on. And then in everything across the exam-wise will be there, and we can work on finishing it out by modules. That said, I want to finish chapter 6 today. Heavy emphasis on proportion testing, and then in a little bit on the chi-squared. I'll overview chi-squared, but I'm not going to ask you more than one or two homework questions on chi-squared. I won't put chi-squared on the exam. That's that. I still have one or two people that had a problem with their exams but haven't emailed me. They might have said they would email me, but they haven't emailed me. And just let me know what's up. And if you need anything, let me know. My emails are coming through. Please, if you do work on a piece of paper and you take a picture of it, before you send me the picture of that piece of paper, read the picture. Right? I keep getting from like 3 or 4 people between all of my classes this beautifully worked out homework, but their phone is not taking it in focus, and I can't do anything with it. Can't say, oh, it's step 2 that's giving you a problem, or it's step 3. I can't see because of the way the phone picture's coming up. So if you take that picture on the phone, open it up in your email, and can I read this? Because I'm not reading the papers on the 3 or 4, and I'm zooming in on the things. In fact, when I zoom in on them, they get blurry. And it's usually not a case of like it's just blurry, which is usually like a handshake on cameras. I have found trying to get a document camera to work for the calculator here, getting cameras to get text digitally is hard when the text is small, eyesight-wise. It's much better to have a steady document camera or a tripod in place, which I have for the camera now. I just need to get a camera that doesn't keep getting canceled on me due to the fact that supply chains are going through. As I'm actually, we had a discussion on supply chains with cars and car sales and how the car lots are used kind of like warehouses for the factories. Well, I was just at a Staples 2 weeks ago. And they had started to say that laptops are actually running out because the supply chain was interrupted when China shut down. And so there's a gap in and so the places that have laptops left over, their warehouses are where they're all coming from, but certain certain outlets have sold all their stock and no new stock is coming in yet. And I think that's what happened with sorry, I was reading Julian's message there. I'll get to that in a second, Julian. Is what I'm having with getting a document camera in. Is it's not one of those things that moves through the supply chain quickly, but as soon as it ran out, and this situation caused a lot of people to get things like document cameras and cameras for doing what I'm trying to do here. And so I just missed that bubble on it. Yeah, Julian, just send me an email where you're trying to get caught up with. I will repeat this. I repeat this through. Grades are due the 13th. If you're graduating, we need to try to get everything wrapped up by the 13th. So we need to communicate and work our way through that. You know, right? This is the type where communication comes through. If you are not graduating, we can take an incomplete, which means that I fill out a ton of paperwork, because everything has a ton of paperwork. That's just life. Yes. And we don't submit the grades on the 13th, but you get an incomplete on your transcript until we finish off the work, and then I submit the grade where it's at after the incomplete is done. So if you're graduating or transferring at the end of this semester, we need to communicate and get all this last stuff in and get out by the 13th is when I need to have them in the book. I think the 11th is when I kind of wrap everything up. Gives me like a day in case, things blow up, which they always do. Usually not in an individual level, but on a per class level. But if that's not the case, we'll look at the incomplete. Warning though, I have people tend to take the incomplete and then just procrastinate more. The real focus we should be wrapping everything up on the 13th. We're almost there. The chunk of stuff we have to talk about is small, and the real work is practicing it in the homework and asking me questions on it. I've got some good questions coming through. Follow up, I see Matt in there. Matt, I had written a reply to one of your email. I haven't heard back. If I missed something, let me know. If you need anything else on that question, please ask it, all right? And this goes with anyone. If you're working on something and you're asking me questions, because email is a delayed format and you're hitting a timeline for that, talk to me, right? Say, I didn't see that yet. Can I have more time? And we know the homework deadlines are pushed forward, and those in-class quizzes have deadlines. If you need anything, though, just keep communicating with me. If you see a deadline pushing on you, and but you're in the work and we have an email chain going, just go ahead. I need another 24 hours, 48 hours, or can you explain this again? People sending the email, we're doing good. I will very, 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 very much so, because this is very big in my 092 class. Not as my 97 class is doing the same thing. And 162 it drives me a little bit batty. If you take pictures of your work on your phone, please make sure you can read it. I'm right now reading someone's homework that I'm really having a hard time struggling reading it. And that's just the nature of the beast here. We can find ways around that. We will find ways around it if need be. All right, so I'm going to get plugged in here. We're going to look at proportions. And proportions really go back to the thing that we started with. I keep referencing chapter 2. I kind of want to say, once you get chapter 2 under your belts, the stuff in chapter 5, 6 is kind of chapter 2 with probability added on top of it. Chapter 2 is our observational statistics. We measure things in the wild, and we label what we see. And then we take this little respite and we go, well, here's how probability works. And if things were truly random, where are the slides? Okay, thanks, Jay. As I get started, let me look up here on this. I thought everything I was talking about was put up. I see what you mean, Jay. Let me... These might actually be... The problem I have with Blackboard on this is I can upload all the signs. Chapter 6, Section 3. But it doesn't automatically create a link, which means it's really hard for me to do this. And then add on top of that, that it doesn't automatically copy to the two sections. So let me put the untouched by my hand chapter 3, chapter 6, section 3 link up into both places, since Jay asked there. Alright, section 2 has it. Let me get it into section 1. And this is my rage with Blackboard. Its interface is archaic, and it does not make adding content easier or harder. It just makes content. All right. Sorry you hear me clicking my mouse running around. Sorry about that. I think these are the right strides. The 7E. Yes. All right. Both slides are now up in sections 1 and 2. It's for section 3 on chapter 6. I'm not going to put the slides up for chapter or section 4. I'm going to talk about the chi-squared stuff rudimentarily, and just give some small questions on chi-squared. Chi-squared is very, very useful if you have a value to compare things against, but for what we're doing, it's not going to be of the greatest importance. All right, slides are up on Blackboard, and I have not touched them, so they shouldn't be a corrupting influence on anyone. All right. So what we're doing is we're looking at proportions, and proportions end up being a frequency. And so what we want to kind of do is we want to find a proportion estimate based off of a variable. And then, again, construct confidence intervals for it. And so it's the probability of success in a single trial of a binomial experiment is P. All right, remember our P's and Q's from before? And, oh my word, why does this do this in my examples? Let me come back down here. Something to do. There we go. I'm going to have to do that periodically. There we go. The point estimate for the P is the chance of success. And so notice we're going to use a P hat here for a sample proportion. And it's the number of successes divided by the number of trials. So that's our estimate. If I have 100 trials and I want a point population proportion of it, we take the number of trials divided by the number of samples. And so that gives us our estimate for success. Right? And so X is the number of successes in N, and Q is the number of failures in N. And they were complements of each other. So to find Q, we use 1 minus P. I hope we can appreciate this is what we were doing with binomial experiments. Right? And we had our binomial equation, which was the NCX times P to the X times Q to the N minus X, right? Which luckily we had binomial tables for coming across, but it was the number of possibilities that we could get these successes to fill out the sample space and how that sample space would come through. So if we want to get an estimate for the amount of success, well, our proportion estimate will be X over N. So, for example, I'm going to do my examples here. If we have a survey, let me switch over to Blackboard and scroll down. If we have a survey of 1,550 adults. So we survey 1,550 adults. And 1,054 say that they use social media. We want to find a proportion of the population that uses social media. And so that will be our P. And we'll say, well, how many successes out of N, or 1,054 out of 1,550, becomes our estimate for this. And this says that 0.68, or 68%, of the population would use social media. Notice, this is the frequency response that we would have gotten from chapter 2 if we're looking at success versus failure. And so an estimate of the chance of success is measuring how many successes you've got in your sample. We're estimating the population though. We're not saying the population is this, we're making an estimate based off of our samples. Well, just like any of the confidence intervals, or any of the things that we have to do with confidence, we have to say how good is this estimate. So we can take our data and we can infer about the population from our experiment. And our inference is what we would assume. If I have so many successes out of the number of people I sample, that is a good estimate for the population. In fact, it's the only estimate we can have because it's the only thing we can see. Our data tells us something about the population. It's all we can see is what our experiment does. Our true step is actually to talk about the confidence of this, to talk about our error, right? So you see how we're going here? We can find a statistic. We can measure that statistic within our samples, and we can have it talk about the population. And that's fine, because that's all we see is what we measure. But when we want to talk about how good that measurement is, then we have to go a little bit further. And that's what we've done in each of these steps. We looked at our population's mean, and we got confidence intervals if we knew the standard deviation, well, using Z critical scores. If we didn't know the population's standard deviation, we had to use t-tables, the students' t-tables, and we got t-critical scores to help us measure our interval range, stating a very particular level of confidence, how confident we wanted to be in the results. And now what we want to do is we want to talk about proportional things, successes or failures in a binomial experiment, and how we can measure that. So we have good estimates for it, but what we want to do now is we want to, well, what's our error? What's our range? How good is it? And so we have to come up with a confidence interval for these proportions. And the confidence interval for the proportions takes the same idea that we had. Notice there's a parallelism to these ideas. And I've said before, one of the things about statistics that can get confusing if you think of it as just a set of equations is picking the right equation to use for the given circumstance you're in. So what we want to do is actually look at the structure that sets up these equations. And our error was the plus minus that we had given a certain confidence level or a certain critical value. And so when we did our errors of our Z scores, our Z confidence level, we had our error calculation with the ZC times the standard deviation over N. Right? We had that square root term coming through. Here, we're using the proportions standard deviation. And if you look back in chapter 5, right, and we look at the standard deviation that we would get from a binomial distribution, it's P times Q, right? And so we can take P times Q, divide by N, and we get error. So we're doing the same thing that we have done earlier in this chapter. We're just doing it with a different type of distribution, specifically a binomial and its P's and Q's. And so we're using this binomial distribution to give our confidence value or our confidence range. And so when you're looking at all of these, which problem, which formula do I use? You kind of have to go, well, what variables am I using, right? If you're using P's and Q's, you're going to pull off of your front matter equation sheet, right? Out of the thing that's in the equation sheet. Let me get back up here. See if I have my front matter. Chapter 6. Here we go. Switch over here. I think that's the right one. So when we look at all of these equations, like, stuff. Right? Which one do we use? Well, you look at what you have. You always start with what you have, and if you have a matching variable for what you have. And I hit the wrong tab here. Let me go back. Where did it go? There it is. Sorry about that. And so if you know the population standard deviation, you're using these confidence intervals. And what's nice I like about these formula sheets is they tell you this. When the population standard deviation is known, it gives you the limits. And then it tells you use this for your error when the population standard deviation is unknown. And notice you're using t-scores instead of z-scores. And then it gets down to here, where we're doing the point estimate for the proportion of success, and it changes the equations for us. And I hope we can see the similarity in error. Error is the critical value times the standard deviation over the square root of n. And if you notice over here, the standard deviation of a binomial distribution was NPQ. And so that pops over into here. Right? So these equations aren't coming out of nowhere. But we're now to the point where we have a lot of them. And so we have to recognize what parts we have as we use them. And I think, to be honest, that's the really big questions that started coming up. When do I use a binomial? When do I use a Poisson? When am I using the z-score versus the t-table? And so we have to keep going back. And again, one of the reasons I do like using this book is they tell you that on the equation sheets. And so you start doing the homework problems, asking these questions to yourself as you put them through. Let's see here. Go back to my slides here. What type of distribution am I working with? Well, I don't know. What do I have? What do I know out of this problem? What is it given to me? And then how does that match what distributions I have? One of the things I kind of have a problem with is the math that makes these equations all kind of comes from the same place. So when I forget one of them, I just recreate it. Which can sometimes be a problem when I'm explaining these choice things. So we go like, oh, see that P times Q up there? Well, that's the standard deviation for a binomial. And then in the end does this thing, and I'm blah, 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 blah. And I'm going on, and I'm like, no, let's look at what we have. And so let's look at what we have here. All right, so let's look at what we can do with this. So the probability that the confidence interval contains your proportion is C. And so that's our confidence value. Notice we get a Z critical value for this, right? So we want to identify your sample statistics. Oh, are we dealing with P? And is our chance of success times n greater than 5? And is our chance of failure times n greater than 5? So we want a large proportion here. We find the point estimate, which is x over n. And then we find the critical value of z that corresponds to the confidence level. So let's go back here. All right, and we find the margin of error. So let's go back to our table here. There you guys are. And so when we look at table 4, B, right down here, level of confidence, your Z-score. See this thing at the end of the so here's table 4, this is table A, and here's table B. Our critical values when we have a given confidence. Now there's another way you could get more exact critical values, because what I want you to notice here is, let's look at 99, right? A critical confidence in 99. It's a double tailed. That means there's 0.5 here and 0.5 here. And so if I come over to 0.5, 0.005 0.005 is 0.0003. 0.25. I'm looking at my table upside down. Here are my two Z scores. Inside of here is 99%. Here is 1%, or the total of the white area is 1%. Let's use the 80. That puts 10% here and 10% here. That means this Z critical point is at 0.9. So we go up here and look for 0.9. It's right here at 1.28. So I can look up these scores if I know where these endpoints are. So if the book asks for a 0.94, right? So let's see if the book asks for a 0.94, that means the total of the white areas is 0.06, with 0.03 here. That means 97% goes up to ZC. So where is 97%? Well, I come to my list of things here, and 97% starts right here, 1.89. 1.89. And so if this was asking me for like a 94, it'd be like 1.89. So these are coming from the Z scores that we used before. But what they've done is they've put together a very common set of them right down here on the bottom. 80% confidence, 90% confidence, 95% confidence, and 99% confidence. But they can be found from the table. That was a rambling way to get there. That slide is all messed up. I thought I fixed that slide. Or is it messed up on your version, Jay? I think the thing that's killing the slides is the animations on them. Whatever they put in there for animations is not working on the modern form of Office. And so what I did is I highlighted it and I deleted it because it seems to double them with the animations coming across. And so we get this kind of weird overtype here. It also seems whenever they add an equation, they add a special frame to it. But it only happened in the stuff from chapter 5 on. And I think it's just a different form of Office. So you see all these P's are in the right place in the sentences, right? But if I come through it one by one, it's doing the animation. All those equations are down, but when I hit everything right in there, they fall into the right place. So it's something with what version of the animation they used, and I think it's an older version of Office, which isn't translating into the filters correctly. I get these directly from Pearson's site. What I might try to do is they have an accessible one, which I think turns off the animations. I'll try to pull those down. And it's hit or miss. It hasn't been on every single slide. So anyway, back to what we want to do. We want to identify how many things we're taking and how many successes we have. From that, we get a point estimate of our chance of success, our binomial estimate. We want to verify that this distribution approximates the normal. So n times p is it greater than or equal to 5. and n times q is it greater than or equal to 5. This is really the same thing that we get with the central limiting theorem, where we want to see n greater than or equal to 30. It's what's happening because these are square roots, and how the n p over q divided by n square root propagates through for n being greater than or equal to 30 for the central limiting theorem. And it is a test to see if we're valid. Then we use that little table to get our confidence value, and we calculate the margin of error. It's no different than the margin of errors we were doing before. We're just focusing on a different part. And we get our two endpoints. So let's do one of these. Let's go through and do one of these. Let me get over to my... Oh, I see. It didn't go back to the slides. So you're saying the slides are all messed up, and I'm showing you the slides are all messed up, and you don't see anything. All right. So here's what I mean about the slides being messed up. It anchors the variables, but if I hit everything through, those p with the hats are in the right place. And I think it has to do with the animations. So I will try to get an animation-less version of it. I might actually send Pearson an email. Give me something to do with Pearson in the evenings, right? Joking. So we want to get our x over n, which was the estimate that we said we had before. We'll have x over n as our estimate. This is a check to make sure the central limit theorem works. And then this was the little table at the bottom that we use. Notice this is no different than what we did in the last two chapters. Or two sections, I should say. We're just focusing on the proportions of success. And so when we find the margin of error, we're going to end up with the p plus or minus. In fact, I still like writing it as plus or minus. I find this a very compact notation over this notation here. Nope. And that gives us our endpoints. So, and here we go again. It is the animated part, isn't it? Let's see here. Well, I'll do what I was planning to do anyway, which I'll do it on the blackboard, because the blackboard is a better place for it. So we're looking at the data from example 1 again. And we want to conduct our margin of our error. So I will pull this data back up. And we had 1,550 adults. And so this was our p-value that we got. We had a 0.68%. And we want to find what our error is in this. Now this should be, remember how I keep saying that margins of errors, we're down elections and polls, this should start looking like poll data, and where we get margin of error in polling data. So let's find our values here. So if p is 0.68, then in q is 1 minus p hat, or 0.32. All right. We have the ability to find our complements. These add up to 1. If I have my chance of success is 68%, my chance of failure should be 32%. In these circumstances, there is no chance of being on the in-between. So let's make sure that these work for us. So n times p, right? We want to make sure this is greater than or equal to 5. So my n was 1,550 adults times 0.68. And that is 1,054, right? Because it is where that came from, and that is greater than 5. Or n times q, should that be greater than or equal to 5? So that's 1,550 times 32. And what does that give us? That gives us 446? 496. 496. Yep. which is also greater than 5. So we have enough samples that we're going to be able to use these statistics. This will be a good estimate, and we have a good confidence level. All right, and so we want a 95% confidence. So our confidence is equal to 0.95. So to calculate E, the error, we have my Z critical times the square root of P times Q over N. P hat times Q hat over N. So let's find Z critical for 0.95. So 0.95 Z critical is 1.96. The critical value is 1.96. So 1.96 times the square root of 0.68 times 0.32 divided by 1,550, which is still under the square root sign. Which, let's get my calculator out here, what, 0, where did it go? There it is. 1.96 times the square root symbol, 0.68 times 0.32 divided by 1550, all within my square root symbol, gives me 0.02322. We're going to keep to there, so approximately 0.023, or if we're talking in percentages, 2.3%. So plus or minus 2.3%. So I could write my chance of success here as 68%. In fact, I'll even be 68.0 plus or minus 2.3%. And so this is what we mean by a proportion value. I'm finding a proportion value for it. All right, let's come back to here. No, that gets us past. Wow, this slide is really messed up. That's everything we just did. All right, we didn't write the endpoints because I didn't put the two values into the endpoints yet. But if I add that 0.203 to my 68, that does give me 70.3. And if I subtract it, it gives me the 0.657. Again, I have a tendency to be a plus minus and not a endpoint person. But I know a lot of the Pearson homework will ask. And we take that plus minus and put it on the end. The neighbor's dog is looking at the UPS man. All right, and so here we're going to look at a figure, and we're going to calculate a 90% interval for the population proportion of 18 to 29-year-olds who get their news from television. So notice we have values here, but we don't just have a P and Q. But we do have a P for our question, don't we? Because the question is from television. So if we're looking for our P value here, P is going to equal 0.27. It's already given for us. And so what we want to do is create our confidence interval for it. And we have 800 adults between 18 to 29. So let's go back and use this data. So one of the things that's nice is P and Q success and failure doesn't necessarily mean you need binary things. If you ask the question in the right way, you can make it binary. And so I have 1, 2, 3, 4 things here, right? But I'm asking, am I going to be one specifically? That makes that one thing my success. The other 3 things become part of the failure. So let's look at our statistics for this. So we had 800 adults surveyed. My p-hat value was 0.27, which means my q-hat, which is 1 minus p-hat, is 0.73. Now, I want to make the range for my values. The first thing I need to do is n times p, is that greater than or equal to 5? Well, n is 800 times 0.27, which is what? 6, carry my 5, 216? And 216 is definitely greater than 5, so we're good there. We pass our test. And q hat is 0.73 times 800. Well, if this is bigger than this, then I know this passes the test. But if we want to, let our calculator do the work for us, this is 584. So I'll be able to make these estimates. I have enough statistics that I can state to some confidence level. And we wanted a 99% confidence. The question asks for a 99. What we can state is the number of people that looked at television, which was 27%. So, all right, my switcher is not switching. My switcher is not switching. So I'm gonna re-explain here what I put up. If you're noticing me, I'm switching between slides, and it seems to be switching back when I pull open the other thing. I'm gonna wind back a couple of steps here. So I brought over the 800, and I brought over this chance of success from the television. So I brought over the 800 adults and the chance of success that they watch television. I then multiplied 800 times the 0.27, and I got 216. Now, when I compared n times q, I knew this was going to be bigger than 216 because this number was bigger than the 0.27. And I just needed these to be bigger than 5 for these statistics to work. Right? So that was all the stuff I was babbling about. I was pointing to this on my slide screen, but my switcher on the stream screen seemed to have jumped back. Okay, so we have a 99% confidence interval, 99% confidence interval. So now I'm going to switch to the browser. There you guys are. And a 99% confidence is 2.575. 99% confidence has a Z critical of 2.575. Sorry for that clicky thing. I know it's right near the microphone. Luckily, I do not use the mouse as much as I should or shouldn't. Still can't find a mouse pad. I don't think I've used one in years. Usually put it on a book. Alright, so we're on the blackboard. So Z critical is equal to 2.575. Z critical is 2.575. So here we pulled the data. We have the criteria we need to make a confidence interval. We have the information we need to get a proportion value from it. So we can talk about a percentage of the population from our survey sample. Remember, that's what these tools are helping us do. I just surveyed 1,500, in this survey, 800 people. I now want to talk about the population of those people based off of our survey. I tested my statistics. I have greater NP and NQ are greater than 5 each. That means I can make these statements with a 99% confidence that I'm going to make. Right? That's what these tools are letting us do. They're letting us measure the confidence of our sample data and let us talk about the population with a 99% confidence. And I'm particularly talking about my sample data. My experiment said 27% of the people get their news from television. I want to talk about the population, and I want to talk about the population getting their news from television. Well, so I'm going to say 27% of the population get their news from television, and I'm 99% confident that 27% will be within the error range of PQ over N, or 2.575 over the square root of 0.27 times 0.73 divided by 800. And let's grab my trusty dusty calculator. 2.575 times the square root 0.27 times 0.73 divided by 800, and 0.0404, or 4%, plus or minus 4%. And so we can talk about this as the percent of our population, right? Our percent of our population that watches or gets their news from television is 27 plus or minus 4%, which means at the lowest it would be 23%, and at the highest it would be 31%. And we can say that with a 99% confidence. I really want to reflect on this, what we have been doing in Chapter 6 here. Because we have gone beyond saying I can measure something. Chapter 2, we start with the idea that we just measure statistics. We grab samples. We want them to be random. Random is the key here, because if we're random, the error spreads out normally. And all of these mathematical rules come from normal distributions or approaching normal distributions, like the t-distribution. So we look at our world. We measure it. And we say, hey, if things are random, what can I talk about things here? Let me get past all these slides here. So I'm going to end on the last part here. Of course. Sorry, I wanted to not leave you on a screen of me saying weird stuff. Oops. There we go. We're going to look at what we need to finish this. The reason I want to do the recap for this, you'll see when I transition over. So we can measure a sample. We can measure something. And we know we're drawing from the greater truth. There's some greater truth out there. We've been pulling from it. And we know what we observe talks about the greater truth. But to understand what we can know about the greater truth, we had to understand randomness. So after chapter 2, we stop for a bit and we did probability. And then we did probability distributions. In fact, chapters 3, 4, and 5 are probability distributions. They're very specific ones. Um, 3 is probability, 4 and 5 is probability distributions. How probability distributes itself depending on if you're counting something or if it's continuous. And so we look at randomness and how randomness works. And we go back to how we observe things. And that's where we are right now. Hey, I observe things. But I observe things randomly. So all of my error should be random. As well, I observed this about my sample. All right, what was the mean of my sample? Well, we can assume that the mean of our population is the mean of the sample, because it's the only thing we can see. But if we've done our jobs right, if we have made sure getting the data is random, then we can talk confidently. We can attach a numerical value to the things we measured. And we can say that we're 99% sure that this range of measurements is valid for that part of our population. And that helps us define how good our observations are. Nowhere in statistics will our confidence ever be 100%. But we can get more and more confident. And you should notice in these examples, when we get more confident, the error gets larger. In fact, if you wanted to say something with 100% confidence in statistics, your error would be infinite. That's how the math works on it. So the closer and closer you get to 100% confident, the larger and the larger your error gets. And what you need to do then is measure more and more and more and more and more. And it's a fight process between how many samples you take and how confident you want to be. The more confident you want to be, but for a narrow range, you need large N. And in all of these, N went up by a square root. So it gets harder and harder to improve this range. But we can at least measure how good our observations are and how good our statements are that we make about the population. Statistics do not just fall out of nowhere, right? And it's the biggest problem with modern statistics, and people that tell you statistics lie, is there are 2 ways they fudge it. And a lot of people don't even know it because they don't take it. They don't learn statistics as a way of measuring the truth. They learn it as a way of conveying something. And when you go to measure the truth, you don't know what the truth is. So you dance around it. People that convey something have an idea of what they think the truth is. And it's a subtle difference. And the first thing that people mess up is they do not observe things randomly. They tend to pick things that are easier to grab data from, right? And a lot of the problems historically with statistics are we used to only ask questions of people that we could converse with. And if you look at how society fragments and fractures itself, that meant that your statistics were really good for people that were just like you, be it racially, socially, economically, culturally, within an area. And so if you want to get past that bias in statistics, you have to find a way of randomly transcending those barriers. Then when you get past that, the means of communicating with people are not always even. The thing that we're just starting to get past is in the age of the cell phone, most of our old political surveys were done by telephone, landlines, because it was a way of guaranteeing the person on the other end. Well, as people transition to something different, that ability to get past the bias in the way you ask them questions had to change. And so that would affect the outcome. The other part of it is in not understanding confidence. I find that as someone who teaches mathematics, and specifically from a scientific background, people expect I have a formula, right? And I plug in the number and I get an answer. The thing is, every measurement has an error in it. Every measurement is a statistic, right? You think you have a ruler and it's a good exact measurement. Your ruler's only as good as the lines on it. And so there's an error. And that error gives you an error in your answer. And so that confidence in how confident you can be of your result, a lot of people don't like to state. They like to say the answer is 3, not 3 plus or minus 0.02. And this is the part I always look for in statistics, and that's what we're looking at now. It's how confident I can be in my answer. And to do that, there's a competition between how wide your interval is going to be and how many samples you take. But because the samples only improve by square root of n, it gets harder and harder and harder to narrow that confidence range without including loads of things. And so that brings me to this last slide. Why don't we go last slide? In the end of each of these sections, we talked about what you need to measure to guarantee a confidence. And so if you want to guarantee a particular confidence, you need to have a critical value that matches your confidence, and you solve this equation, the n times the p times q over that critical value divided by the margin of error you want to give. And this tells you go out and measure this many n. So when you go to set up a survey and you will say you want to be within, well, we're going to use one of these. So I'll come over here. So we're going to take this equation and we're going to use it. Right? And this formula assumes you have an estimate for P and Q, but you might not. It's not a bad estimate to assume that it's going to be 50-50 if you don't. And that's what we're going to do. So let's come over here and use this on the blackboard. So I want to do an experiment. And I need to know how many surveys I need to take. And I want my margin of error to be within 1%. All right? I need that. I need to be able to convince someone of something. I need a low margin of error. So let me rewrite this equation here to find the n we need. So we need n equals p q times my critical value over my margin of error squared. So we have to find an experiment, and we need to be able to say how many n we need to go. So I need to be accurate, and I need to be sure. So I want to be within 1%, and I want to be 99% confident of the results I get. And we're going to say we don't know what P or Q are, so we're going to use the estimate of 0.5 times 0.5. All right, we're going to say it's 50-50. This actually drives the largest number of possible n's. If your estimates were different, if you're like saying 60% and 40%, that would be 0.6 times 0.4. It's less than this. This will give you the most. In fact, when I was taught this, it was, even if you thought you knew what P and Q was, use this, because it'll give you the most n that you need. All right, so let's figure out how many n we need to give a 1% error. So down here is going to go 0.01 with a 99% confidence. So over here, I'm going to go to my z-score. Z-table, 99, 2.575. 2.575. So 2.575. Z critical equals 2.575. So 2.575 squared. All right. So 0.5 times 0.5 times parenthesis 2.575 divided by 0.01 quantity squared. And I need 16,576.5, so we'll round up 16577. Look at that. To have a 1% error, a plus or minus 1% on a percentage estimate with a 99% confidence, I need 16,577 samples. That's why when you see these political surveys, they're looking at like a 5% error. Because 5% error only needs about 800 to 2,000. And this is the conflict in designing an experiment. How small do you make your error versus the effort, the money, and the cost of measuring large N? And I'm shouting and I'm really loud. This is really important. This is the crux of confidence levels. It's the crux of interpreting the statistics that people are giving. Is that the more accurate you want that to describe the population, you want it to be random, and you need a large N to narrow that gap. So when you talk about your statistics, you should have three things. You should have a guarantee of randomness. You should have some confidence interval. You don't have one value, but you have an interval, and you have the actual confidence itself, right? And so you will probably hear me call confidence intervals error. It's the plus or minus in error that we have. All right, this wraps up the section on confidence intervals. I said I was going to touch on chi-squared. Chi-squared is optional at MWCC. If you have the StatWay class, I don't think anyone else covers chi-squared. I tend to like to cover chi-squared because STEM students have to know chi-squared, but I do teach that in my physics when I do it. So I'm not going to touch 6-4. I'll even drop the homework questions on it. But definitely this percentage and this percentage interval is very important in knowing this. So we finished Chapter 5 and Chapter 6. And we'll have the exam for 5 and 6 up online. But it won't be due until the end of the semester. I'm putting all the due dates. I'll have the homework scheduled to match the lectures, and all the homework will be up. And we're going to do Chapter 7 and Chapter 9 to end. Chapter 7 and 9. Hypothesis testing is on for people, and it's how we can make decisions. And so I want to use the last 5 minutes that I'm going to have here to kind of go where we are. I know you're just staring at some screens from me here, but I did want to tie this all together. When we first talked about statistics, I said it was the mathematics of observing things. And we went from, hey, we don't know what reality is, to we can look at reality and we can measure what we see. We should appreciate what we see is not everything. Right, and I'll even go, I always like using the example of light. We only see invisible light. There are X-rays, there's infrared, there's ultraviolet, there's radio. They're all part of light. We only see a part of it. And it took us a lot of experiment and observation to realize the full extent of light. So when we see something, history and technique and how scientific method is done has realized we don't see everything. So statistics as a mathematical science takes that into account. We observe something, it's a sample, and we can now infer about our population with our samples. We had to make sure we were measuring randomly. Once we measure randomly, we can make inferences. We have now did our probability distributions to do things randomly, and we're now talking about how confident we can infer about the truth from what we observe. The last part of the scientific method, why we observe things, why we make formulas and rules, is we want to make decisions based on what is true or not true. We want to make a hypothesis and we want to test it. And that's what we're going to move into next, is testing our decisions. Just, hey, I have observed something new. Is that new thing valid enough for me to change what I knew before? Do I know enough to update what I know? We need to make a decision. We're going to learn the statistics of making decisions. and that's called hypothesis testing, and that's chapter 7. And we're going to move into that. But there's been a pattern, and it's all been matching what we talked about in the first 2 classes. That we're going to observe things. We're going to tell you how good our observations were at telling us what the truth is, and that's where we ended now. And then we're going to make decisions. We're going to update what we know. That's a decision based off of what we observed. And we're doing it all with the ability to put numbers behind that. All right. That's it for me. Have a good one.